Start at the top here, heating only system. A heating only system is using one piece of plant to do one job. This box will do heating and cooling out of the box. It's, you know, that's how you buy it. So a heating only system only does one thing, and is therefore more embodied carbon to do that one thing than it would otherwise be. If you use a comparison of coefficient of performance, and this is my rant you might have seen before, but the air source standard rating point for coefficient of performance is 7 degrees on the source and 35 degrees on the load, whereas the ground source rating point is 0 degrees on the source and 35 degrees on the load. Now this 7 degrees in our winter is more like an average air temperature, high average actually in the UK, whereas 0 degrees on a ground loop is a minimum kind of temperature. So because the efficiency of heat pumps is predicated by the difference between the source temperature and the load temperature, the bigger the gap, the bigger the electrical consumption, the harder the thing's working. This coefficient of performance measure is just not a level playing field at all. Okay. If you then look at seasonal COP, so that's the annual heat delivered divided by the annual electrical consumption, that's a much fairer comparison between the two systems. So that's the first thing. Next thing. Heat pump replacement cycles, you could very easily justify to somebody who doesn't know any better that ground source is going to last, the ground source heat pump system is going to last the same amount of time as an air source heat pump system. They're both heat pumps. Massive difference though is that this thing is in the plant room, in a nice warm plant room that doesn't get rained on and leaves blowing into it and so on, whereas the air source is outside. So that's another thing. A lot of people overcomplicate header systems, so you've got all sorts of manifolds, valving, and all that kind of stuff in there. Very often see sand being used to encase all these headers, which is common if you're putting water pipes or gas pipes in the ground, but for ground source, actually, it's not part of the best practice. Part of the embodied carbon calc is around the installation, and you could assume that your ground source installation is all diesel powered, where in actual fact, a lot of it, particularly in city centre sites, is now electrical powered. Assessments of the ground loop requirements by rules of thumb, which very often overestimate how much pipe you need in the ground. One of the big ones that I've seen is that I've actually seen consultant engineers assume that these boreholes are lined all the way down in steel that's left in there. Well, actually, you would never do ground source like that. It would just be too expensive apart from anything else. So we don't, that's part of it. Another one that is quite high in embodied carbon is concrete. So assuming that all of this is filled up with concrete. I've very often seen in the carbon calcs that they've actually got, instead of a percentage of antifreeze in the loop, the glycol, it's 100% glycol. It's high in embodied carbon, that stuff. And then bigger borehole diameters than we actually use as well is very often part of it. So if you want to, either willfully or through ignorance, want to make ground source look bad, that's how you do it. So first thing we do is we try and do heating and cooling whenever we can. The same bits of kit do heating and cooling. So you're, plant-wise, halving your embodied carbon in round numbers. Obviously, you want to model your performance properly. And one of the key things that people forget is that the defrost cycle on air source, so the coils outside that are sucking heat out of the air are cold. Condensation therefore happens. That condensation freezes and it needs to be defrosted. Basically, that's defrosted by electrical energy. So your coefficient of performance during defrost cycle heads very close to 1. So it's effectively a direct electric heater at that point. Proper replacement cycles, ground source 25 years a heat pump should last, air source in our country 15 years, something like that. It does range depending on whether you're close to the coast or not. So you might be, if you're in, where you are in Newquay, you might be down at a 12-year cycle for an air source before it just starts falling apart. Keeping your header arrangements minimal, it's just good engineering, keeping it simple, no brainer really. As I said earlier, fully or partially electric borehole installation. We don't fill these trenches with anything special. We just use the backfill material. So we're reducing muck away, as they call it, so stuff taken off site. And we're also not bringing in clean materials in there. Properly designed borehole, so not a rule of thumb. Temporary casing, anything that's put in the ground during installation in terms of casing that borehole is taken out. Thermally enhanced ground only when needed. So a lot of times in these boreholes, what we can do, if we've got groundwater, let's say our groundwater level's about here somewhere, what we can assume therefore is that all of this in here, if we fill that with gravel, it's going to be full of water. And so that's a brilliant medium for energy transfer. And we're only putting this grout plug in at the top, the cement plug in at the top, to stop anything really getting down that borehole. That's the reason for it being there, and to stabilize the ground around the borehole as well. Correct fluid specification, instead of 100% glycol, we're talking typically between 20-22%. I'm working on the Barclays campus up in Cheshire at the minute, and they want to get rid of glycol entirely out of their ground, which is entirely feasible if the properties are right. And again, proper borehole diameters, less than 150 mil is what we're excavating out of the ground. You can imagine, if you've got a big column of soil like that, as opposed to 150 mil, you're taking more stuff out of the ground, therefore you're taking more off-site and so on.